Good afternoon, everybody. We finally get close to the end of this course. And today's lecture is about, today's and tomorrow's lecture is about sensors of flow rate and level. I hope I will manage to keep this lecture, all the topics into this lecture, so that tomorrow we can make some exercise for the final exam. Basically, it's not really sure yet how the final exam will be, and I refer to the if the exam will be in presence here or remote. Definitely, we will have soon the second test, and the second test will be as the first one in Moodle. But for the final exam, it would be much better to have a proper exam in presence, so you should be here, because typically you have to solve some little problem, make some calculation, and doing it remote is not so simple. But of course, everything depends on the restrictions we will have in January and February. And this is something definitely we cannot predict now. It seems, fortunately, the situation is getting better. So now, according to the new rules, students can come only for consultation for the final thesis. Yet you cannot come for regular lectures, and of course, we still don't know for the exam, but if the situation will get better by the end of the semester, probably it might be possible to have a traditional exam here, of course, respecting the social distancing and all the hygienic measures we have to put in place to protect everybody. Just to be safe, so of course, the type of the final exam will depend on the style of exam we will have. So if it's a remote exam, it will be different than having an exam with you here present at school. But just to be sure, I will present every week, starting from now, some short exercise similar, or at least an example of what you might find at the final exam. So that in case you have the exam here present at school, you will be prepared, okay? In case it will not be possible, we will study other methods for the final exam. Last semester, for those who were not here, for the exchange students who didn't experience the final exam here at school last semester, eventually, we were able to host the exams here at school, so it was not a problem. Let's hope that the situation will improve and we will be able to meet again here at the faculty. Fine. Before starting with the sensor and sensors of flow rate and level lecture, I would like to talk very briefly. And of course, I always say that I will talk very briefly, and eventually I talk half an hour, but this time I will try really to be brief, about an interesting topic, which I discovered while reading some of the reports you sent me about the laboratory. It's an interesting topic because it's something which is not commonly explained. Typically, we try to give information to the students, but not methods. And at least this virtual laboratory, where I make you some question about phenomena that I observe in the laboratory and that I show you in the video, are somehow tricky. And for some of them, for some of you, sometimes it's not easy to answer those questions, especially because they require some methods that is not so common. One of the questions I've done during a laboratory was this. I was amplifying the voltage of a thermocouple. So I had my thermocouple here. As you know, the thermocouple, well, still don't know because it will be topic of the next lecture next week, but I've already explained in the laboratory that, in the virtual laboratory, because you were not with me there, that you have an output voltage which is proportional to the difference of the temperature between the hot and the cold end, and amplify this, this voltage using an inverting amplifier, which is something that we have studied multiple times now, okay? Let's say that we want to amplify it 100 times. Here, the output will be V2 equal R2 R1 negative R2 R1 times V1. Now, I've shown you in the laboratory that, for instance, if you want to select, to amplify by 100 times the voltage V1, you can select two resistors, R2 and R1, whose ratio is 100. So you can select R1, which is R2, R1, let's say it's 1 kilo ohm, and R2, 100 kilo ohms. Or you can select 100 ohms and 10 kilo ohms. Or, for instance, 10 ohms and 1 kilo ohms, okay? In all these three cases, you have R2, which is 100 times bigger than R1. 100 kilo versus 1 kilo, 10 kilo versus 100 ohms, and 1 kilo ohms versus 10 ohms. The ratio is always 100. So you expect to multiply, so the gain here is 100, you expect to multiply V1 always times minus 100, and the voltage should be always the same. Unfortunately, it turns out that the output voltage in the first case is about minus 283.7 millivolts. In the second case was minus 233.5 millivolts. And in the third case was minus 89.8 millivolts, okay? So despite the gain being always the same, we get three different voltages, which sometimes are very, very different. I mean, like here we have about 90 millivolts and here 284. That's quite a difference. And the question of the laboratory was, okay, tell me why. The responses of two students were very interesting. One told me, well, we are using an operation amplifier which is not ideal. In real life, we don't have ideal operation amplifier. We have an operation amplifier which, for instance, has a bias current. So we have studied that a component of the output voltage depends on the bias current, for instance. And we know that if we have, for instance, a bias current here in the negative input, the output, there is a component of the output voltage which depends on the bias current. So you have an output voltage. I will put here prime to show that is the part of the output voltage which depends on the bias current, which will be given by the bias current in the negative input, let's call it IN, times the resistance R2. I won't prove why it is so. We have already studied it many lectures ago. Then this student told me, well, fine, you always have the same bias current because it's a feature of the operation amplifier. And once you increase the resistance R2, you will have a bigger component caused by the bias current. The bigger is R2, the bigger is the component of the output due to the bias current. Just to be clear, it's not the whole V2. V2 includes a component which is given by V1 amplified by the gain of the amplifier, which is the ideal response of an operational amplifier. Plus, you will have, for instance, this component, V2 prime, which is caused by the bias current. And the explanation of the student was, okay, let's say that here, I'm simplifying, but in this case, we have the, quote marks, correct value, and then as you increase R2, you increase this additional component of V2, which is given by the non-ideality, represented by the bias current. Now, technically speaking, it is true that you have a larger component in the output given by the bias current if you have a bigger resistance R2. But is this the cause of the difference we observe at the output? And here's the point. The phenomenon itself is true, but that's not enough. You must prove that this phenomenon is able to justify what you observe here at the output. So let's put down some numbers. This operational amplifier, if you go to the datasheet, had a bias current which is about, well, maximum, let's say 4 nanoamperes. Typical value, give it or take it, 1 nanoamperes, okay? So, what happens if you have R2, which is 1 kilo ohms, or R2, which is 100 kilo ohms? V2 prime will be 1 kilo times 1 kilo ohms times 1 nanoamperes. It's 1 microvolts, sorry. If you have 100 kilo, you still have the same bias current, but multiply times 1 kilo ohms, it will be 100 microvolts. So, yes, definitely, you have this component in the output, which is 100 times bigger if you have 100 kilo ohms instead of 1 kilo ohm. But the difference is so small. It's 100 microvolts against 1 microvolt, which is really, really a small difference. Here you observe a difference which is much bigger. You go from 90 millivolts to 284 millivolts. So you have roughly 200 millivolts of difference. So definitely this difference given by the bias current cannot justify the difference we observe at the output. Because here we have a change, a difference of 100 and 100 microvolts. Here we have 200 millivolts. We are observing a change in the output which is 3 orders of magnitude bigger. So yes, the phenomenon itself is true, but once you plug the numbers, no, that is not what causes the change in the output we observe. So this is important to show that it's not enough to mention a phenomenon which is true in theory. You are also in practice, because this is not only theory, this is practice. You must always connect to put, you must always put down the numbers, make some calculation, and prove that this is actually causing what you are observing. In this case, it was not true, because once you make some calculation, you find out that it is almost negligible, the effect. So the effect is there, but it's very small. Another student, oops, now let's erase this. Another student had the opposite approach. Well, actually, I erased also some part which I needed. Here it was 284 millivolts. Here 234 millivolts, and here about 90 millivolts. Okay, I just approximate to the to 1 millivolt. The other student was using a different approach. Was telling me, okay, again simplifying. This is the correct value, and then when I go down to lower resistance, there is a problem. Why there is a problem? Because I use low resistances. Low resistances means bigger current, and therefore I'm loading the operational amplifier. True? Well, definitely, if you have smaller resistances, you have bigger currents. But let's try to calculate them. So again, let's take the two extreme cases. How do you calculate the current which is generated by the operational amplifier? Well, here you have an output voltage which is basically exposed to infinite input impedance because you have a voltmeter, and the voltmeter doesn't absorb any current, okay? So the current that you observe here getting out is the current which goes to R2. And you can calculate it because basically here you have the same voltage V2, because here you have a virtual short circuit, and here the current is 0, and here is the current which comes from the thermocouple. So the output voltage here, V2, is the same voltage applied to this resistance, and you can calculate, for instance, in the first case, you have 284, so the current will be 284 volts divided by 100 kilo ohms, which means that you have 2.84 microamperes, if I didn't make any mistake. Yes. And in this case, I get a current which is 0.09 volts, because you have 90 millivolts, divided by 1 kilo ohm. Okay? So it's about 90 microamperes. Again, is it true that if you use a lower resistance in the feedback, you get a bigger current? Yes, definitely. Because here we have 90 microamperes versus, oh, sorry, here is point, not dot. It's dot, not comma. Definitely we have 90 microamperes versus 2.8, let's say 3 microamperes. So definitely it's much larger, the current. Nevertheless, this is not enough to justify overloading of the operational amplifier. This student was saying, okay, larger current, you are overloading the output of the operational amplifier. Not really, because this operational amplifier can generate currents up to 20, 25 milliamps. So again, the phenomenon itself is true. Nevertheless, once you put the number and make some calculation, once you put down the numbers, you find out that this difference is definitely true, but still we don't go to values of current which might tell me, okay, this is a current too large to be produced by the operational amplifier, and therefore eventually the voltage drops out because it's not able to produce such a current as the circuit would require. And also he was mentioning about the resistance changing with temperature, because again, larger current, you have Joule effect. Therefore, the resistance warms up, and the value of the resistance changes because of temperature. Again, it is true, but here we are using a current which is so small that the power involved in this, the power released by this resistor is very, very small. So the effect itself is basically negligible. I don't know, maybe we can make some calculation. Probably briefing on the resistor has a bigger effect. Again, nothing to be ashamed about these problems. On the contrary, these laboratories are useful exactly for this reason, because we share opinion, we share solutions, and therefore we can step by step fix these problems. What I wanted to say is that in any case, not only for these exercises, but for all your career, the other exams, and later when you will work, you must always try not only to find a principle, a physical principle, because the physical principle itself might be correct, as I've shown you here, but you have also to calculate the effect you expect from this principle. You have to take some numbers, make sometimes some estimation of the quantity you expect. They don't need to be so precise. When I calculated the bias current here, I got 1 nanoamperes, might be 4, but you know, it doesn't matter. You make some ballpark number and you calculate more or less how much is the effect. If you see that it's in the same order of magnitude, then you can try to make some more precise calculation. But if you see that the effect is several orders of magnitude smaller than what you observe, then you don't need to make very precise calculation. You just realize that it's too small to justify what you're saying, what you're seeing. Okay? So this is very important. Every time you send me some report from the laboratory, don't just tell me this is the reason and that's it. You have just also to prove it. You have to tell me why. For instance, here you see an output voltage which is changing, even if theoretically I should not. And if you tell me it's because of the bias current, fine, put down some numbers and prove that this is the reason why this happens, okay? In some other cases, this is not necessary, true, but if you can justify your theory, always do it with some numbers, okay? And of course, this applies in all technical fields. If somebody turns out with a solution for a problem, yeah, the first thing you have to do is to ask, fine, true, this is true, but does your theory hold also with numbers? Let's make some calculation. And then eventually you find out that these magical solutions, most of the times, in real life, they don't work once you make some calculations. Okay, as usual, again, I talked for half an hour. I apologize. Now, let's start with talking about sensors of flow, rate, and level. And we start with the sensor which, surprisingly, doesn't have anything electric. So it's just a sensor of flow, which is based on gravity. It's called rotameter, and it's composed of a pipe which has a cross-section, not constant. Maybe I should throw it not in 3D, but in 2D to show better. Now, I'm extremely emphasizing the fact that the cross-section here, the diameter, is smaller than the diameter here. Okay? Inside, you have a floating object like this, floating object, which will have a force given by the gravity, and a force given by the fact that you have some flux. Can you actually see the screen? Because, oh, no, there's some problem on the screen. Can you see the screen? Please tell me if you can see the screen. This is a problem if we cannot see the screen. Okay, yeah, in fact you cannot see the screen. So which is, okay, maybe now it will work. Yes, it went standby. Now you should get it. So if I see it there, it means that you also get it on YouTube. So, okay. Screen is black. Yes, maybe there is some delay. And because now I see it's going out. I really apologize for this inconvenience. Now it works. Okay, fine. I apologize for this inconvenience, but of course we try to do our best. Now, there is a flow of any type of fluid, and this flow, of course, causes a force which pushes the floating object. How did I call it there? FF, fluid force. So from one side you have the gravity force, which is pushing the floating object down, and of course you have the force given by the fluid which tries to push the floating object up. Now, in this image I show you that if you have the floating object down, then the area between the floating object and the cylinder, which is not really cylinder because it's not straight but inclined, the tube, let's call it tube, not a cylinder. The space between the tube and the floating object is smaller. So you have a larger force given by the fluid flowing in the tube. Why? Because the mass of the fluid must pass through the floating object and the cylinder and the pipe and the tube, and there's not much space, so it has to sneak around. There's not much space, so it will give much more force. If, on the contrary, the floating object is on the top, well, there is a large space, so it doesn't create the flow doesn't create a large force, because, well, there is a lot of space, so no problem, can pass. So, what happens? If I have a low flux, I have, well, or better, let's start over. The floating point will stop when the two forces, the force given by the gravity and the force given by the fluid, the flow, will be in equilibrium. Okay? If the two forces are in equilibrium, then it doesn't move anymore. There's no reason to move if they are in equilibrium. But, and where do you find this equilibrium? Well, the force given by the gravity is always the same, because the mass of this object is always the same. So, in order to find equilibrium, you must have a force given by the flow, which is always the same, and accidentally always equal to the force given by the gravity. So I want always the same force. But how can I get always the same force if I have a variable flux? Well, if the flux is low, the flow meter will be here at the top, at the bottom. Because true, we have a low flux, but we have also a small space where this flux can pass through. Okay? So low flux, true, but also low space. So the effect of that low flux is sort of amplified because it doesn't have much space to pass through. On the contrary, if I have the same rotameter, so this is for low flux of the fluid. On the contrary, if I have a large flux, again, I want the same force, but the flux is bigger. So if you keep if you had the floating object here on the bottom, would cause a force too large. So how can I compensate the fact that I have a larger flux and have the same force? Well, you make the space where the flux passes through bigger. And you achieve that if you are at an higher level. Okay? Here, yes, I have a bigger flux, but also bigger space where the fluid can pass through. Okay? And therefore, it compensates. You can either have a low flux here, but also low cross-section, or you can have a large flux and also large cross-section. Totally, they will give you always the same flux, the same force. Okay. These are two typical examples of rotameters. So you just install them. Of course, the advantage is that you don't need any power because there is nothing electric there. But unfortunately, you should always remember that you must install them vertically because they are based on gravity. If you install them horizontally, as soon as you get a minimum flux, boom, you get to the maximum of the scale. Fine. Next, let's talk about turbine flow meter, which is straightforward. You have pedals. You have a turbine where you have a fluid which passes through the pipe, and then you have some pedals which are moved by the flow. And how can you detect it? For instance, you have a magnetic sensor here at the top. So you have you can measure. You have typically a structure which is ferromagnetic inside. As it rotates, you can detect pulses of magnetic field with a magnetic sensor, and then you know how many rotations you had, which correspond to the volume of the fluid which made this turbine rotate. The first problem is that it has some threshold. What does it mean? It means that if you have a very little flow, the fluid can pass through the turbine without making it rotating. It has some inertia. So if the flow is not large enough, is not strong enough to even make the rotation start, which is not something really good if you want to, for instance, install this flow meter to sell, for instance, water to your customer. Why? Because then your customer would open the tap of the water just a little amount so that the water can sneak around the turbine without having the force large enough to make the turbine rotate, because you need a minimum force to make the turbine overcome the inertia and start actually rotating. And then, of course, they would open slightly the tap, and still the water slowly. Another issue you should take into account is that you have some rotating object inside the pipe, and when you have a rotating object, mechanical object is always a mess because something can go wrong, and but also they affect the flow. Well, in some cases they even stabilize the flow, but generally speaking, you are changing the flow that you want to measure, and again, you introduce an element which changes the system that you want to measure. Another alternative, if you want to avoid putting an object right here in the middle, you can measure it on the edge with some other paddle wheel fluorometer. A very interesting phenomenon is the one used by a flow meter based on vortex. Basically, it's based on an object which you put inside the place where the liquid, where the flow, also not necessarily the liquid, any type of fluid, also gas. You want to measure the stream off, the flux off, and when you have this buff here inside, it will create some vortex. So if you have here a velocity of fluid from the left-hand side going in this direction, the fluid will have to go around this object, which obstructs the flow that you want to measure, and it will create some vortex. This vortex then will move to the right-hand side. So just imagine that you have this object here, you have some water, some other fluid which arrives from this side, then it will cross the object and it will make one vortex and it will move. Then another vortex, and then again and again and again. So you have this stream of vortices which appear after this bluff that you have here, which obstructs the flow, and therefore which creates these vortices. What you do is to put an object, for instance, a sensor which measures the pressure, and every time you have, for instance, a vortex, for instance this one, the vortex 3, which arrives from this side, there will be a difference of pressure between the right and the left-hand side, so that you have you can detect it with this pressure meter. So just imagine that you have some cantilever like this, then you have a vortex which passes through and it moves the cantilever. Then you have another vortex on the other side, it moves the cantilever. So every time, again, let me see if I can do it like this, okay? No, I shouldn't show telephone numbers on internet. So just imagine that here there is the object, here there are the, okay, this way. Just imagine that here there is the object creating the vortices, and then you have the vortices which go to the left and to the right of this cantilever. Okay, every time you have a vortex, this cantilever will move to the left or the right according to the difference of pressure created by the vortex. Okay, so just imagine that you have a vortex here, vortex here. Okay, no, it was not a question. And then it will create, it will make this cantilever move, and we have already studied how to measure this deformation using strain gauges, for instances, or other systems. And as it turns out, you can measure the frequency of these vortices, which depend on the velocity of the fluid. So if there's no velocity, if there's no stream of fluid, then you don't have any vortices. But as soon as the flow starts increasing, you will have more and more vortices appearing after this object in the middle, and therefore you have the frequency of this cantilever that increases, and from this frequency you can, in fact, linearly recalculate the velocity of the fluid. Another system to measure flow is based on ultrasonic effect. So this works because you have a pair of transmitter and receiver. Well, there are different systems how to measure with ultrasonic waves, but this is the most common to understand, the most common and easiest to understand. It's based on the fact that if you have a transmitter here, T1, and the receiver here, R2, you generate from the transmitter an ultrasound, which goes from T1 to the receiver, R2, and it will take some time to go from the transmitter, T1, to the receiver, R2. Then you have another transmitter, T2, which creates another ultrasound, which goes to the receiver, R1. If, again, I start having cough. If there is no flow, the time the signal will take from T1 to R2 is equal to the time it takes to go on the way back from R2 from T2 to R1. Why? Because the distance is the same, it's the same ultrasound, it takes the same time, the speed is the same, there's no difference whatsoever. But what happens if you have a fluid flowing in this pipe, for instance in this direction, from the left-hand side to the right-hand side? Then the time of the red ultrasound, the one which goes from the transmitter T2 to the receiver R1, will be different from the time it takes from T1 to R2. Why? Because one is going in kind of the same direction of the stream, and the other is fighting against the stream. Okay? So here you have your pipe, here you have your fluid. One ultrasound is going this direction, which means that it has a component, the component of the speed, in this direction, is parallel, has the same direction as the flow. Okay? So this one will be faster. When you are going on the opposite way, then you are fighting against the flow. Now, of course, you are not going entirely in this direction, and that's why here you have the cosine of alpha, where alpha is the angle between this direction and the direction of the flow. Okay, so this is the angle alpha. So what you observe this phenomenon on the component that you have parallel to the direction of the flow. This tells you that, of course, if you have the transmitter and the receiver orthogonal to the flow, to the direction of the flow, this effect doesn't work anymore. Okay? Because it will have the same time going from the top to the bottom as from the bottom to the top. Okay? So there's no difference whatsoever because they are orthogonal to the flow direction, and that's the same. But if there is an angle which is not 90 degrees but somewhere in the middle, then you have a component of the velocity which can be either in the same direction or opposite to the direction of the flow. So one, let's say, again, simplify, one ultrasound is helped by the fluid, by the stream of fluid, the other is opposed, and therefore you will have a difference of time, which tells you, which gives you the information about the velocity of the fluid. Now, if you want to amplify this effect, you can have multiple reflections, so for instance you can have the transmitters and the repeaters here and here, then here the ultrasound is reflected, and you have the same effect but for a longer path, despite, sorry, having the pipe always do the same diameter. Okay? A very, very interesting, by the way, if meanwhile you see that the screen disappears again, just let me know, because I might forget about that, because I see it on my screen. I have it also here on actually physically, but if it disappears, maybe I don't realize. Now, another flow meter is based on a physical principle we have studied already multiple times. If you have a fluid, for instance water from the tap, I should remember to bring water. Sorry, I apologize. If you have a fluid, for instance water from the tap, which contains ions, then, and this is typical, like if you watch any analysis of water, even the water that you buy at the supermarket, you see that there are ions on the labels. So if you have water, which or generally speaking, any fluid which contains ions, what you can do is to expose this fluid to a magnetic field, and then you know very well what happens when you have a magnetic field exposed to a charge, to an electric charge, which moves. You have a force which is proportional to the speed of the charge, right? So just imagine that here you have a pipe where you have positive and negative charges. In this case, I represented them by two colors, brown or orange, whatever it is, and purple. Then they are mixed together because they don't have any reason to be separated. But once they arrive under a yoke where you create a magnetic field, then the negative and the positive charges go in opposite direction. The negative will go on one side and the positive will go on the other side. Why? Well, because you have force to positive and negative charges, which is opposite. Okay? So all the charges, positive and negative, first are mixed together, messy around. Then, once they arrive under the magnetic field, the positive and negative go one on one side and one to the other side. And then after once they leave this region with the magnetic field, they return back together because, again, there's no magnetic field anymore, giving them the force to keep separated. So, once you are here under this yoke, you will have a concentration of electric charges, negative on one side, positive on the other side. And what you can do simply is to detect them, putting two electrodes here on the opposite sides, so that you can measure a voltage given by the disequilibrium of the charges. Okay? More negative charges on one side, more positive charges on the other side, you have a voltage. Again, the principle is the same that I explained for the whole effect sensor. It's true that there is this force which is generated by the magnetic field on moving charges, which keeps them apart, positive on one side and negative on the other side. But as soon as you keep positive and negative charges aside, then you develop an electric force, because opposite charges try to attract each other. So they find an equilibrium point where the force given by the magnetic field and the velocity, of course, is equal, which keep the force, the magnetic force, which keep the charges far away. It's equal to the force which tries to attract them back. Once you have this equilibrium, then you have the charges which are at this concentration to the left and to the right. If you have a larger speed, you have a larger, if you have a larger speed, you have a larger magnetic force, right? Because the force is given by the speed, magnetic field. So you will have a larger magnetic force, which makes the charges go more far away to have a larger electric force because of more distance to counterbalance the larger magnetic force. Okay, so that is the reason why at the end of the day I find the voltage at these two terminals, which is giving me an information about the velocity of this stream. Okay. One of the big advantages of this sensor is that it doesn't have any moving part. Well, there are the charges which move, but we don't count them as moving parts. So it is less probably it will fail. But on the other hand, of course, you have to take into account that the response depends on the fluid that you have. Okay, so if you have suddenly a change of the charges which are found in the fluid, then you will have a different response. Typically, this is just the basic principle of the induction flow meter, because in reality it doesn't work like that. Why? Well, because you don't really want to keep always positive charges on one side and negative charges on the other side. Why? Because that is the best recipe for having some corrosion on one of the terminals. There are chemical reactions that occur if you bring positive or negative charges always on one side, on the other side. So much better is to flip the polarity. Okay, so you can have a magnetic field which is either pointing up or pointing down. So periodically you generate a magnetic field which is either pointing down or pointing up. You flip it. You generate it with a coil, for instance, in the yoke, and you periodically flip the direction. So if you flip the direction, so in one case you will have, oh no, this is not correct. Let me do it better. Okay, let me draw it like this, okay? So just imagine that you have positive and negative charges mixed here and here. Then, in one case, you have the charges, the positive charges going to the left and the left one and the negative one to the right. And if you change the direction of the field, it's inversed. Okay? Positive and negative. According to the direction of the magnetic field, now I'm watching from the top, okay? I'm just describing on the blackboard here these charges which are mixed before arriving under the yoke. They are mixed later and they separate because of the magnetic force once they arrive under the magnetic field. So what you are doing is to generate a magnetic field which points to the up or points down. And according to the direction, up or down of the magnetic field, the electrons, the positive charges and the negative charges go either to the right or to the left, or vice versa. Okay? So every time you change the polarity of the magnetic field, the two streams of charges, negative and positive, cross. Okay? So first the negative charges go to the right, the positive go to the left, and then once you change the polarity of the magnetic field, boom, they change. Which means also that you change the polarity of the output voltage. Okay? If the negative charges go to the left, to the right, and sorry, if the negative charges go to the right and the positive to the left, you get one voltage. If you flip the polarity of magnetic field, you flip also the direction of the charges, then you get a different voltage, okay? So once you take here a voltmeter, you can either measure a positive or negative voltage according to the direction of the charges. In this case, you avoid having always charge with the same sign on the same electrode and mess it up from the chemical point of view. But it's also important because then you can detect the output voltage which depends only on this effect. Now there could be some funny chemical reaction inside the pipe, inside the flow meter. And it could give you some component of the voltage which is not given by the I apologize, which is not given by the velocity of flux itself. Okay? It's a voltage which is there even if you don't have any flux, simply because you have some electrochemical reaction. Okay? So how can you understand if the voltage that you observe at the output of the flow meter is given by the flow itself, which generates magnetic force and therefore separation of charges, or if it's given by some electrochemical reaction inside the pipe? Well, if it's a voltage caused by the flow of charges in the fluid, it will change with the same frequency you change the magnetic field. If you change the polarity with 10 Hertz, you will have an output voltage which will change at 10 Hertz. If you change it at 22.3 Hertz, then you will, if you change the polarity of the magnetic field at 22.3 Hertz, then you will have an output which will change at 22.3 Hertz. So if you have a constant value of the voltage given by other causes, then you don't account for that because you know that the output will be only at that specific frequency that you're using. And this is a typical example I've already mentioned several times. Sometimes you use a frequency as a number plate for the signal. If you have here 1 kilohertz as carrier of your signal, you know that at the output your signal will be at 1 kilohertz. Whatever you see which is not at 1 kilohertz, then you know automatically is not carrying signal. It's given by something else. It's given by some interference. It's given by some electrochemical reaction in the pipe, whatever. You don't care. You care only about the component 1 kilohertz because you know that the output should be at 1 kilohertz. And that is a very simple, well, of course, if it's your wrong day and you don't have much luck, you might have some interference also at 1 kilohertz. And therefore, in that case, the principle doesn't apply. So that's why typically you select a frequency which is not a common frequency where you can find some other component of the noise. So definitely you don't select 50 Hertz because definitely you would sum your signal to anything which works at 50 Hertz, at least here. If you go to other countries, you have 60 Hertz. But this is a very important principle. If you use a DC magnetic field, you will find a DC voltage, or at least a voltage DC proportional to the velocity. But in this way, you cannot distinguish between DC voltages caused by the flow and DC voltages caused by other phenomena, which are there always present at the terminations of the at the contacts here, which measures the voltage. If you, on the contrary, flip the magnetic field at specific frequency, you know that the output should be at that specific frequency, and therefore you can distinguish from other sources which have not that frequency. Now, try to speed up. Other flow meters. There are pitot tubes. How do they work? Let's assume that you have a tube here in the center of this pipe, and which collects the flow, the pressure given by the flow here at the center. And we measure the difference between this pressure, this dynamic pressure, the pressure given by the flow, which moves inside the pipe. We measure the difference between this dynamic pressure and the static pressure, the pressure that you have also if you don't have any stream. You have a pipe, you have some pressure. If you take the pipes of your flat, there is some water carrying, going around, you have some bar of pressure inside the pipes, fine. And you have that pressure even if you don't have any flow, so you cannot measure that pressure as a measurement of flow, because it's a static pressure. It's a pressure that you have anyhow, even without flow. So, here on the side, you measure the static pressure, orthogonal to the direction of the flow, and that's the first pressure. Then you have a tube here in the center, which measures the dynamic pressure, which is the pressure given by the fact that you have a flow which enters in this tube, and will have a pressure P2, and then of course you have a differential pressure transducer, something that we have already studied maybe last week, something like that. You remember, you have a membrane, you have a capacitor, differential capacitor. The membrane moves to the left or to the right according to which pressure is bigger, P1 or P2. So if the pressure here is bigger than the pressure here, then the membrane, instead of being in the center, it will curve to that side. Okay, so if you remember, you have capacitor here, which is fixed, capacitor here, which is fixed, and then you have a membrane in the middle. If the pressure here, P1, is bigger than the pressure P2, okay, P1 is bigger than P2, then this membrane will definitely move, it will bend like this because of the larger pressure P1, and therefore the capacity C1 will be lower than the capacity C2. And again, it's something that we have already studied. Another differential pressure flow meter is based on the fact that we have a restriction on the pipe. Okay, so just imagine, again, fluidodynamic is not my major, but I will try my best to explain how this works. Again, we have to find a difference of pressure which depends on the flow. Okay, so let's say that we have a pipe with some obstruction here, and we measure the pressure here and here, just before and after this obstruction, this part here. Now, if there is no flow, the pressure is everywhere the same. You have the static pressure in your pipe, fine. But what happens if you have a flow in this direction, right? Then here you have a larger pressure because all the fluid arrives here and it has to squeeze down again, I use squeeze. I know technically it's not correct, but I try to simplify. So here all the fluid tries to go through this obstruction. So here you will have a larger pressure, and here you will have a lower pressure. Okay. So just imagine all the flow which pumps up here and has to go through this smaller diameter. And of course, we will have a pressure 1, P1, bigger than P2, only when we have a flow, and of course, it will give us information of how large is this flow, okay? Another way to measure flow is to use some device inside here, which moves if there is some flow. So just imagine that you have this this device here in the middle. As you have a flow in this direction, it will deflect. Of course, there are mechanical systems here to resist to this deflection. And again, how to measure the deflection? You can use strain gauges. Now, all these systems, well, I'm not sure if I have all of them, but I guess so. Definitely the turbine, as I mentioned already before, have some threshold, which means that they have a mechanical inertia, at least those that have a mechanical part. And for low fluid, for low flux, the flow itself doesn't have force enough to start the mechanical part moving. And therefore, you have some threshold, and if the flow is below that threshold, you cannot measure it. The response is 0, despite there is some flow, which is little. So not only you have problems of linearity, whatever, but you have also a problem that you cannot measure below some fluid, because technically the sensor doesn't work. This problem is solved with the oval gear flow meter. Here you see an example. Again, it is based on mechanical parts. How does it work? You have these two gears. Here in the photo probably you can see it better, which rotate, for instance, this one clockwise, and the second one, the horizontal one, counterclockwise. Okay? Now, what happens? How does it work? Let's say that you inject some water, and this green one rotates clockwise. So you are in this position, then it rotates. The red one, rotates counterclockwise, until finally the water arrives on the top. And then, as you rotate again, the water will go out. Okay? In the meantime, now here I highlighted only the side on the highlighted only the water on the left hand side, but keep in mind that also there is some water coming from the right hand side. Okay, so once you're here, the water enters from this pipe. Then once you're here, there will be some water on this right hand side space, and after I expel the water brought up by the green gear, then it will be time for the water brought up from the right gear to go out. And meanwhile, again, there will be some water which pumps up here, and in the next step you will have this amount which entered, which will go here on the left hand side, and it will be brought up and expelled as usual. Okay. So it works both left and right hand side. When you are in this condition, you have some water which enters in the top, and then as it rotates, it will be brought up either to the left or to the right, alternatively, and expelled from the upper side of the gear. What is the advantage? The advantage is that now, well, the principle itself is that for every turn, you know exactly the quantity of water which passes from one side, from the bottom side to the top side of the flow meter, simply because it corresponds to this volume, right? So once the gear is in this position, you know that the amount of water which will be expelled from the top side is corresponding to the volume of this half moon here on the left-hand side. It's a volume that you can calculate, and you precisely know for each rotation how much water goes to the other side. So you have multiples of this volume, which is brought from one side to the other side. So you just know, you just calculate how many rotations you had, and that corresponds to the multiple of volume which goes to the other side. What is the advantage? Is that there is no way for the water to sneak around the sensor and go to the other side. The only way the water can pass from the bottom to the top side, from one side to the other side of the flow meter, is to be trapped between the gear and the external container, okay, in this alpha moon, let's say, and be brought up in this way. There is no space for the water to go to sneak around, right? So if the flow meter doesn't rotate, there is no way that you can have some flow of water going to the other side. Does it have an inertia? Absolutely. You have some mechanical parts, you have some gears, and definitely they have an inertia. If the flow is too small, if you don't have pressure enough to give the force to these gears to rotate, well, they don't rotate. But, contrary to the turbine, for instance, if they don't rotate, there is also no stream of water. If you have a turbine with a pedal, then all this water can sneak around and go to the other side. In the oval gear flow meter, this doesn't happen. If the flow is small and it doesn't have the force to make the gear rotate, simply the gear does not rotate and there's no flow of water. This means that it's not, sometimes it's not able to measure liter flow. Sure, there is still a threshold of flow that is not able, or no, this is not precisely correct. There's a threshold of pressure, let's put it this way. So if the pressure is not enough, it will not rotate, so you don't have a flow. Which means that still you need some force to make the gear rotate. Still there is some inertia. But there is no way there could be a flow small enough to go to the other side, but not large enough to start rotating the pedal. That's why this is used, for instance, if you want to measure some flow and charge how much you're selling to your customer, okay? Now, I still have 15 minutes. Let's see if I manage to solve it. Another way to measure the flow is to use a thermistor inside the fluid. What is a thermistor? We will study it next week. It's a sensor of temperature, and the resistance of the sensor depends on the temperature. So what you do is to inject a current in the thermistor, which is large enough to generate some heat thanks to Joule effect. So you warm up the resistor, and then if there is a stream, for instance, of water, this water will cool down the thermistor, the resistor, by bringing away the heat. So if you have no flow, the heat will be there. There is no cooling effect given by the water, and therefore you have a temperature. If the water cools down the thermistor, the, temperature decreases, and therefore also the temperature decreases. Typically, also the resistance changes, sorry. Typically, you have a negative thermistor, which has a resistance which decreases if you increase the temperature. If you have a normal resistor and you plot the dependence of the voltage on the current, then you have a straight line. You know it very well. It's a constant resistance, and in this characteristic, the derivative, the slope of the characteristic is the value of the resistance. If the resistance is constant, you have a constant slope, and therefore you have a straight line. In a thermistor, it doesn't work like that. Why? Because you have heat produced by the current when the current is large enough to produce heat, or to produce a significant amount of heat. This means that at high current, you have large temperature, right? And if you have large temperature, you have a lower resistance, which means that for high current, lower resistance means lower slope. That's what we observe here. You don't have a straight line anymore, but you have a line which curves down because the slope becomes lower since you have a lower resistance. Then, if you have a stream of water, for instance, or any other fluid which cools down, then what happens? For the same current, you cool down the effect, you remove the heat, you cool down the resistance, you remove the heat given by the current, and theoretically, if the flow of the fluid, the flux of fluid is large enough to remove all the heat, then you would be back on an ideal resistor which has a straight line. Generally speaking, the larger the flow, the flux of fluid will be, the larger will be the cooling, therefore the larger will be the resistance, and finally the larger will be the slope of this line. Okay? So just imagine that you're here. Let me see. So just imagine that you inject some current, you have a resistance which depends negatively to the temperature. So you inject some current, you are here, because you warm up the resistance and you get a lower resistance. Then you have some stream of water. The stream of water brings the heat away, therefore the temperature decreases, and therefore the resistance increases. And if you watch it in the voltage current graph, so let's say this is point A and this is point B, right? So you have the current, you have the voltage, you inject a current which is large enough to generate some heating. So this is, let's call it RA, and this is RB. So RA is the slope of this line, of this characteristic in this point. Then you cool it down, therefore the resistance increases, which means that you are on another characteristic. So yeah, you have on this point, and the slope here will be larger. Okay? what you can do then is to set a constant value of current and observe the change of voltage given by the cooling of the fluid which passes through the pipe and cools down the thermistor, okay? Another system, well, this is one way to use this sensor. You inject a current, a constant current, and then you observe the voltage. But of course, we can do better. Why? Because we can keep the temperature constant. In this case, we simply have, you generate some heat, and you observe the change of the resistance caused by the heat produced by the current on one side and the cooling produced by the stream of fluid on the other side. But again, here we have a system which is, we have a resistance which is not linear to the temperature. What can we do to improve the linearity? As we have learned last week, we can use feedback. So we keep the working point always the same. We keep the sensor working always at the same working point. In this case, we keep the resistor, the thermistor, working always at the same temperature. So, how can I keep the thermistor working always at the same temperature? Well, you use this bridge. Again, this is a bridge even if it's drawn horizontally, but it's the same system as vertically. So we have 4 resistors. 3 of them are resistors which do not depend on the temperature. They can be outside the pipe, basically. And they are constant resistors at the value of the resistor that you want to keep the thermistor at. For instance, let's say that we want to keep the temperature here, and we select 3 resistors of the bridge corresponding to RA. Then you have a thermistor, of course, and if the temperature is, let's call it TA, then the output of the bridge, which is taken between these 2 middle points, will be 0, because you have a bridge with 4 resistors, all of the same value, RA, and therefore you get 4 resistances which are the same, and you get 0 output voltage. What you do is to monitor this voltage with the controller. The moment you have a larger flux cooling down the thermistor, then the resistance increases, right? It means that you have cooling, more cooling, so the temperature decreases. What should you do to keep the temperature constant if there is a larger cooling effect given by a larger stream of water? Well, you have to increase the current. Therefore, with the regulator, here you inject bigger current so that it will give an extra heat to compensate the fact that now there is a larger stream of fluid cooling down. So now we have a larger stream of water, it cools down more, so I have to give an extra heat so that finally my thermistor will be at the same temperature. On the other way, if there is a lower stream, then I have to reduce the current, because now the cooling is lower. So I reduce the current so that again I have less cooling, fine, but also less current. So at the end of the day, I have the same temperature at the sensor. Okay. In this way, what you do is not to measure the resistance itself, is not to measure the voltage output of the bridge as a measurement of the stream of water. What you do is to measure the amount of current you have to inject in the resistor, in the thermistor, to have always the same temperature. And this depends on the stream that you have on the water on the pipe, okay? Let's see how much more. Yes, definitely I'm not able to finish this, but it's almost at the end of the lecture. So I will finish tomorrow this part of the lecture, but it's really not much, maybe 20 minutes. And so that's unfortunately the end of this lecture. So finally, tomorrow we end this lecture, and then we make some exercise. So please try to check at home, try to solve the exercises, and so that tomorrow you see if the solution you tried to calculate is correct or not. Okay? Well, as usual, if you have any question, you can also contact me personally. Okay? Well, with some of you I've already talked on MS Teams, so it seems it works. Sometimes you can even prefer to talk personally rather than making question public. Okay, so see you tomorrow. Enjoy your afternoon, and as usual, stay safe.